Hi everyone and welcome to this episode of Kuiper Labs. In today's video we're going to be discussing bond enthalpies and the delta H for a reaction. So we're going to define what we mean by bond enthalpy. We're going to describe or kind of flesh that out by discussing average bond enthalpy, and we're going to be comparing the bond enthalpies for different types of covalent bonds. And then we're going to bring it back and connect it to delta H for a reaction. So seeing how these two things relate to one another, and then go through a couple of worked examples of how this plays out. So firstly, what do we mean by bond enthalpy? Okay, so we talked about enthalpy as this energy content in a system. And so what we're then articulating is saying, all right, well, the energy content of a system relates to the bonds between the atoms of the particles we're discussing. And so one of the things that we recognize is that we need to put energy in to break a covalent bond. So we need energy input because we're going from a stable connected state to an unstable state of the separate atoms. Okay, the flip side of that though is that when we form a new covalent bond, that energy is released because we're doing the reverse. We're going from unstable separate atoms to stable combined or bonded atoms. Okay, so there's energy going in to break them, energy coming out when we make them. But there is the same amount of energy involved for a particular covalent bond. So saying, okay, if I take a carbon and a hydrogen atom, if they're connected together, a certain amount of energy is needed to pull them apart. That same amount of energy is released when we put them together. Okay? But the idea is that this does depend on the nature or the specific covalent bond we're talking about, because that relates to what are the atoms, how big are they, how do they go in sharing their electrons, how close can they be to each other, can they be close or have to be far away? So those sort of specifics will affect how much energy is involved in either breaking or making that type of covalent bond. But so that's what we mean by bond enthalpy. So the average bond enthalpy is the average amount of energy needed to break 1 mole of a specific bond type to give separated fragments when they're all in gas phase. Okay, so when the molecules are separate from each other, and saying, okay, well, how much energy do we need to take all those covalent bonds, 1 mole of them, and break them all apart? How much energy is required? Okay, so for example, carbon-hydrogen, if we have 1 mole of carbon and hydrogen bonds needing breaking, then it's 413 kilojoules required. Okay, 1 mole of carbon-chlorine bonds, though, is 346 kilojoules. So it's easier to break the carbon-chlorine bond than it is to break a carbon-hydrogen bond. Now, one of the things to keep in mind is that often it is difficult to measure these exact values. Okay, you can't just kind of stick a probe in and kind of work it out. But we can use the approach of Hess's law that we've looked at previously in order to calculate or determine them. Okay, so we can look at this idea and actually kind of assign values to all of the pieces, all of the bonds that are involved. Okay, so the size of the bond enthalpy, its magnitude, relates to what we call the strength of the covalent bond. Okay, so more bond energy or bond enthalpy, a higher bond enthalpy is a stronger bond because more energy is needed to actually break it apart. Okay, so if you look at the values in the table here, so for carbon-hydrogen it's 413, but for a carbon double bonded to oxygen it's 743. Now, it kind of makes sense in some ways because we've got 2 bonds that we're actually trying to break here, and likewise with oxygen as well. But it then means that we need to account for this, or we need to factor it in when we're thinking about the energy we've got to put in to get a reaction to occur, the energy we get out when the new bonds are formed. Okay? So, the delta H for a reaction, delta RH, can be estimated from the average bond enthalpies. Okay, we've looked at in the past by looking at enthalpy of formation of particular compounds and estimating it that way. This is a different strategy. Okay, so the total energy required to break all of the bonds apart can be estimated by adding them all together. So, 4 carbon-hydrogen bonds, 2 carbon-chlorine bonds, etc. We add all of those pieces together for the total energy to break bonds. And then we look at the total energy released by making bonds, same sort of way. We add all of those bonds together. Okay, and the difference between these two values, the red and the blue, is the overall change in enthalpy for that reaction, the delta HR. Okay, but the thing to keep in mind is that they're likely to be different from the actual value, so that this is an estimate and it's as such is imperfect, because average bond enthalpies for the same bond can be different quite significantly from one another depending on how we actually calculate those numbers. Okay, so the actual numbers that we're relying on may not be accurate in themselves. And also, that then we're talking averages, which means that in a particular compound, maybe the arrangement of the atoms means that the energy is higher or lower than the average. Okay, and so if we're assuming the average, then that value is going to be incorrect. Okay, and it can be quite a significant difference as well. All right, so now if we have a look, let's see this in action. Let's see an example, and we're going to look at the formation of carbon dioxide from carbon monoxide and an extra oxygen atom, a half O2. Okay, so we've looked at these values before, and we said, all right, so this change involves a delta H of minus 283 kilojoules for every mole that reacts. Okay, so and that's negative, which means that energy is released overall. Okay, so it's exothermic. And so that means that there's more energy stored in here than is stored in here, and the difference leaves the system. Okay, so now let's look at it in terms of bond enthalpies. Okay, so breaking this, there's a triple bond in here, breaking that bond, and then half of this bond, because we're looking at a half here, so those are our red energy input, and then we're making two carbon-oxygen double bonds, the blue. Okay, so the difference between the red and blue is our delta H. So if we now actually input some values here based on what we know, okay, so we're saying, all right, the energy from the breaking all of the bonds is 1319 kilojoules. The energy released by making new bonds is minus 1598 kilojoules. So adding these two things together, breaking and making, we get minus 279 kilojoules for every mole. Okay, so it's not exactly the same. It is close, like in terms of, you know, when we're considering real world estimates, we could accept that, but we need to recognize that it's not exactly the same, that you need to be careful there, but it is a strategy that can help us to be able to actually determine these things. Okay, so let's have a look at another example. I'll walk you through the process for a particular example. So we start off by writing out the balanced chemical equation, particularly using structures, Lewis structures or line structures where we can, so that we can see all the covalent bonds present in both reactants and products. Okay, so we can see, all right, well, how many bonds are we breaking and making? Okay, calculate all the energy required to break all the bonds in the reactants. Okay, if we're imagining that the bond, you know, the elements being like Lego pieces, how much energy do we need to break them all apart from each other before we can start rebuilding? Calculate the total energy that will be released when we make those new bonds, all of them in the products. And then look at the difference from reactants to products. Okay, so if that value is positive, it means it's endothermic. If it's negative, it means it's exothermic. Okay, so this is the process that we follow. Okay, so let's look at this reaction. We've got a reaction with this compound methane with chlorine gas, and we're swapping one chlorine atom with one hydrogen atom to leave our products over here. We'll call chloromethane and hydrogen chloride. Okay, so these red ones are the ones that we're breaking, the blue ones are the ones we are making. Okay, so using the values that we have here for average bond enthalpies. Okay, so the energy from the breaking those bonds, this carbon-hydrogen, this chlorine-chlorine, is 678 kilojoules. The energy we get out from making these bonds is minus 798 kilojoules per mole. Okay, now remember, so these values, the red values are positive because it's energy going into the system. These blue values are negative because it's energy coming out of the system. Okay, adding these two things together, we get minus 120 kilojoules for every mole. So what that's saying is overall that this reaction will release 120 kilojoules per mole into the surroundings. Okay, so it's exothermic. Alright, so we introduced what we mean by bond enthalpy, the energy that's involved in either breaking or making a particular covalent bond. The energy in to break it, energy out when we make it. And seeing how average bond enthalpy is when we're considering, alright, the possible bonds in a compound, we're averaging it out. And seeing that it can be different to the real world value. When comparing bond enthalpies from one type of covalent bond to another, it helps us to identify how strong or weak they are, relatively speaking. And then we looked at how we can actually use these average bond enthalpies to calculate the delta H for a reaction and showed you an example of how it's done. Alright, thanks very much for watching. Bye for now.